Hello everyone and welcome to the coronavirus edition of the 9th lecture of our signal theory class. In this lecture we will learn about the Z-transform. The Z-transform is essentially the Laplace transform for the discrete signals and systems. To get a formula for the Z-transform, I will start with the Laplace transform and then I will turn it into the Z-transform by sampling the signal. This is the formula for the Laplace transform, and here I indicate sampling of this continuous time signal. This is my sample time, my sampling period is Ts, and this is my sampled signal, which we denote like this. Now when I substitute this discrete time into the formula for the Laplace transform, the continuous time signal will become a discrete signal, and instead of this t, I will have n times ts. Also, because these signals are no longer time continuous, I will no longer integrate, but I will need to sum. Here I can rewrite this exponential like this, and this expression in the bracket I will denote as z. So at the end I will get this, which is the definition of the Z-transform of signal x of n. We also denote it as uppercase x of z, which we also refer to as the Z-transform image of the lowercase x of n. So remember, this formula, this Z-transform, has the same meaning as the Laplace transform, but for the discrete signals and systems. Consequently, it can be used for similar things, so the rest of the lecture will follow a similar pattern that we had with the Laplace transform. First, we need to take a look at some basic properties of the Z-transform. As with the Laplace transform, this is a bit long and rather boring, but again we have to get through it. First, the correspondence between the Z-transform and the Fourier transform. Let's assume that my signal is 0 for negative time, and this is its Z-transform. If the signal is 0 for negative time, this is how I can write its discrete time Fourier transform. Now, what do I need to do to turn this expression into this one? This is what I need to do. If I substitute e to the j omega for z, and my signal is 0 for negative time, this will turn the z image of my signal to the discrete time Fourier spectrum of my signal. Next, the Z-transform of the Dirac delta pulse. When you substitute into the definition formula and use the fact that the Dirac delta pulse is 0 everywhere except at n is equal to 0, where it is 1, you will get this result. So the Z-transform of the Dirac delta pulse is 1. Next, the Z-transform of the unit step. When you substitute into the definition formula, you get this. Here the unit step actually has no effect because for n greater or equal to 0, the unit step is 1. So this sum is just a sum of an infinite geometric series which is equal to this. Or you can write it like this. And this sum will converge when the absolute value of the inverse of z is less than 1. Now the Z-transform of a geometric series. This is the substitution into the definition integral. Here you can leave out the unit step and you can combine this expression and this expression into this single expression. Here you again have a sum of an infinite geometric series, which is this, or you can write it like this. And this sum will converge when this condition holds. Next, the Z-transform of a signal delayed by m samples, where this m is assumed to be positive. This is actually somewhat equivalent to the formula for the Laplace transform of a derivative. Remember, for the time-continuous systems we had differential equations that contained derivatives, while for the discrete time systems we had difference equations that contained time delays. So while for the time-continuous systems we needed to deal with derivatives, for the discrete time systems we need to deal with the time delays. Thus the Z-transform of a time delay. Here I substitute it into the definition formula. Now I will use this substitution, which will give me this expression. In this expression, I can split this expression into these two expressions, and I can extract this expression in front of the sum, which will give me this. Here, I will break this sum into these two sums. The first sum will contain the positive values of k, and the second sum will contain the negative values of k. And this first sum is actually just the z transform of my signal x without the time shift. This second term contains the first m values of x of n before time 0. These are actually equivalent to what we had with the Laplace transform as the initial conditions. But here the initial conditions are not the signal and its derivative at 0, but they are some values of our signal before time 0. Now, if we assume that these initial conditions are 0, which we do quite often with discrete systems, we will get this expression. So the z transform of a signal delayed by m samples will be the z transform of a signal which is not delayed, but it is multiplied by z to the power of minus m. The delay by m samples gives you the multiplication by z to the minus m. Now the linear combination. When you apply the z transform to the linear combination of two signals, and you crunch, you will get that it is the same linear combination of the z transforms of the individual signals. So when you have a linear combination of signals, you can apply the z transform directly to these individual signals. Here I show what happens when in time domain you multiply your signal by this geometric series. When you substitute into the definition formula, you can combine this expression and this expression, which will give you this. And this is just the z transform of your signal x, except not at z, but at z times a to the minus 1. So the multiplication by this geometric series in the time domain will cause this scaling of z in the z image of your signal. Last, the z transform of a sine and cosine. These are a bit ugly, but you do not need to remember them. So when you want to compute the z transform of a cosine, you write the definition formula, then break the cosine into the sum of two complex exponentials, and break this sum into two, one for each exponential. Now, each of these expressions is a sum of an infinite geometric series, which is equal to this and this. These two fractions can be combined, and they will give you this expression. The z transform of a sine is derived in pretty much the same way, and you will get that it is this expression. Okay, so these are all the z transform properties we need right now. As with the Laplace transform, you need to learn this except for the z transform of sine and cosine, which I will show you how to avoid. Now let's take a look at an example where we use the z transform. Here I have a simple filter, a simple discrete system, and I would like to know what is the output of this filter if this is the input. How do I do this? First, I need to write down the difference equation of this filter. You should know how to do that from lecture 5. Now I will apply the z transform to this difference equation. On the left and right hand sides of this equation, I have linear combinations of my signals, so I can apply the z transform to the individual signals. The z transform of y of n will become the capital Y of z. The z transform of y of n minus 1 will be the capital Y of z, but because of this time delay, it will be multiplied by the z to the minus 1. I assume that the initial conditions are 0, so this time delay will turn only into this multiplication by the z to the minus 1. On the right hand side, I will do the same thing. This x of n will become the capital X of z, and this x of n minus 1 will become this capital X of z, but because of this time delay, it will be multiplied by this z to the minus 1. Now on the left hand side, I can extract this y of z, and on the right hand side, I can extract this x of z, and that will give me this. Now I can divide by this polynomial, which will give me this expression. Here I can see that the z-image of my output signal is given as the z-image of my input signal multiplied by this function. As with the Laplace transform, we call this function the transfer function. Now, if I want to find what is the output signal in the time domain, I need to substitute for this x of z and compute the inverse z transform. First, this x of z is the z transform of this input signal. When you use this formula, you will get this z transform. Here I have it substituted. Now the inverse z transform is done in similar fashion as the inverse Laplace transform. First you need to break this function into partial fractions, and then you do the inverse z transform of the individual partial fractions. However, here you need to be cautious because here you have negative powers of z. Basically you have two options. The first option is that you will get rid of these negative powers of z by multiplying the numerator and the denominator by z to a sufficient positive power. In this case, if I multiplied both numerator and denominator by z to the power of 2, I would end up with only positive powers of z. And now I could break this function into partial fractions. But this typically gives you longer computation and unnecessary computational steps. Easier way to do this is to actually work with this z to the minus 1 as if it was a single variable. If it helps you, you can replace all the occurrences of the z to the minus 1 with some variable q and work with that. When I do that, that is when I work with z to the minus 1 as if it was a single variable, I can break this function into these partial fractions. And these constants a and b I can compute using the cover-up rule. This polynomial has the root at z to the minus 1 equal to minus 2. So I cover it up and I substitute minus 2 to the rest of the expression, which will give me this, which is equal to 2. This polynomial has the root at z to the minus 1 equal to 4, so I cover it up, and I substitute number 4 to the rest of the expression, which will give me this, which is equal to minus 1. So this is my decomposition to the partial fractions. Now to take the inverse z transform, I need this property of the z transform. This partial fraction actually corresponds to this fraction where this a is equal to minus 1 over 2. And this is the z transform of this geometric series. So this partial fraction is the z transform of this expression. Similarly, this partial fraction is the z transform of this expression. So the inverse z transform of this entire expression is this expression, and this is the output of my system when I have this signal at its input. Overall, you can see that the way I use the z transform is quite similar to the way we use the Laplace transform. Now let's take a look at how it will go for a general second order system. This is the difference equation of a general second order system, and these are what for the z transform we call the zero initial conditions. Now when I apply the z transform to this difference equation, I get this. The y of n will become this uppercase y of z. This y of n minus 1 will become this uppercase y of z multiplied by z to the minus 1, and this y of n minus 2 will become this uppercase y of z multiplied by z to the minus 2. The right hand side is transformed in a similar fashion. Now on the left hand side I can extract y of z, and on the right hand side I can extract x of z, which will give me this. Here I can divide by this polynomial, which will give me this expression. And here you can see that for a general second order system, the z image of the output is given as the z image of the input multiplied by this function of z, which we call the transfer function. Here the transfer function is written in the negative powers of z, but you can multiply the numerator and the denominator by z to the power of 2, which will turn it into this form where you have positive powers of z. This first form we usually use for the computation of the inverse z transform, and this second form we usually use for the computation of poles and zeros. As with the Laplace transform, we need to take a look at how the transfer function is related to the impulse response frequency characteristic and stability. If I have a discrete system and I want to know its impulse response, I need to feed it the Dirac delta pulse, which at the output will give me the impulse response of the system. Now, what does this look like in the z domain? The z transform of the Dirac delta pulse is 1, and the z image of the output is supposed to be the z transform of the input multiplied by the transfer function. If the input is the Dirac delta pulse, this is 1, so the z image of the output is the transfer function. That means the z transform of the impulse response is the transfer function. The z transform of the impulse response is the transfer function. Moreover, a real-world system will not start to output any non-zero values before this Dirac delta pulse arrives at its input at time 0. So this impulse response is 0 for negative time. Consequently, from the equivalence between the z transform and the Fourier transform, if I substitute e to the j omega for z, I will get this h of e to the j omega, which is the Fourier transform of the impulse response, which is the frequency characteristic of the system. So when you have a transfer function and you substitute e to the j omega for z, you get the frequency characteristic of a system. That is quite useful when I want to find out what kind of filtering my system provides, when I want to find out if it is a low pass, high pass, or whatever pass. In addition, if I know the transfer function, and I know that the transfer function is the z transform of the impulse response, I can use the transfer function to judge the stability of the system. This is how I can do it. With the system described by a difference equation shown on the previous slide, you will get the transfer function in the form of a rational polynomial function. In the rational polynomial function, you can factor the polynomials in the numerator and in the denominator and decompose this rational polynomial function into partial fractions. As with the Laplace transform, the roots of the polynomial in the numerator we call zeros, because when z is equal to one of these roots, the transfer function is 0. For example, if z is equal to this z sub z1, the transfer function is 0. The roots of the polynomial in the denominator we call the poles. The poles are the points where the transfer function goes to infinity. For example, if z goes to this z sub p1 or z goes to this z sub p2, the denominator goes to 0 and this transfer function goes to infinity. So you can break this rational polynomial function into these partial fractions, and the impulse response would be the inverse z transform of these partial fractions. To compute the inverse z transform of these partial fractions, I need to use these two formulas. And I need to adjust these partial fractions to fit this form. To do that, I need to multiply both the numerator and the denominator by z to the minus 1, which will give me this. Now, this form corresponds to this form, except I have this multiplication by z to the minus 1 in the numerator. But multiplication by z to the minus 1 in the z domain corresponds to the time shift in the time domain. So this is the z image of geometric series where this minus 1 is here because of this z to the minus 1. And this is the z image of this geometric series where this minus 1 is here because of this z to the minus 1. And of course this constant is easy, that is just a z transform of a Dirac delta pulse. When I put it all together, this is the inverse z transform of my transfer function, so this is my impulse response. Now for the system to be stable, I need its impulse response to be stable. I need this impulse response not to diverge to some infinity, and that will happen only if the absolute value of these poles, z sub p1 and z sub p2, is less than 1. Remember, when you have a complex number and you compute its power, you can express it like this. Here the magnitude of this expression is always 1, and this part just changes the phase of the complex number. It will be this part that will decide if with growing n, this number goes to 0 or to infinity. If this absolute value is less than 1, then when n goes to infinity, this expression will go to 0. But if this magnitude is more than 1, when n goes to infinity, this expression will also go to infinity. So you need the absolute values of these poles z sub p1 and z sub p2 to be less than 1 for this impulse response to be stable. If both these poles z sub p1 and z sub p2 have their magnitude less than 1, this geometric series and this geometric series will asymptotically approach 0 as the time goes to infinity, and the impulse response of this system will be stable. However, if either of these poles z sub p1 and z sub p2 has magnitude greater than 1, for example, if this pole z sub p2 has its magnitude greater than 1, as n goes to infinity, this geometric series will diverge to infinity as well, and the impulse response will be unstable. Therefore, for the system to be stable, the poles of the transfer function need to have their magnitude less than 1. So, when you plot the poles of the transfer function into a complex plane, and they all fall into the circle with unit radius, where their magnitude is less than 1, the system will be stable. However, if only one pole falls outside this circle with unit radius, the system will be unstable. If the poles fall exactly on this circle, the system will be marginally stable. This is actually equivalent to what we had with the Laplace transform, but now instead of the left-hand side of the complex plane, the stability happens when the poles fall within this circle with radius 1. A bit of nomenclature. This circle is typically called a unit circle, and this plane where we draw the values of z we call the z-plane. On this slide, we will learn how to sketch a quick guess of an amplitude frequency characteristic when we know the zeros and poles of the transfer function. I will demonstrate on the transfer function from this example. I will use this transfer function. From the previous slides, you know that I can take the transfer function, substitute e to the j omega for z, and that will give me the frequency characteristic of my system. And I can take this and plot it in MATLAB, which will give me this. Now, similarly to the Laplace transform, I can use the poles and zeros to quickly get an approximate sketch of this frequency characteristic even without MATLAB. As with the Laplace transform, I first need to find what the zeros and poles of my transfer function are and then plot them into the complex plane. To find the zeros and poles of a transfer function in the z-domain, it is usually best to put the transfer function into the form where I have only positive powers of z. To get there, I need to multiply both the numerator and the denominator of this transfer function by z. When I do that, I will get this. So this transfer function has 0 at 1 because when I substitute 1 here, the entire transfer function will be 0. And this transfer function has a pole at minus 1 over 2 because when I substitute minus 1 over 2 here, the entire transfer function will be infinite. When I plot these zeros and poles into the z-plane, I get this. This is my 0 and this is my pole. Now remember, in the plot of the magnitude of the transfer function, this pole will create an infinitely tall hill and this 0 will create a valley. Here I have it indicated with these contours. The red contours indicate the hill around this pole and the blue contours indicate the valley around this 0. If you're wondering what this looks like in 3D, this is what it looks like in 3D. this is the hill created by this pole, and this is the valley created by this zero. Now, with the Laplace transform, I got the frequency characteristic by tracing the magnitude of the transfer function over the imaginary axis. This was because with the Laplace transform, I needed to substitute j omega for s to get the frequency characteristic from the transfer function. With the Z transform, the substitution that gives me the frequency characteristic from the transfer function is this. I need to substitute e to the j omega for Z. Now, what part of the complex plane do I get when I substitute e to the j omega for Z? Well, this is an expression of a complex number with unit magnitude and phase omega. So this substitution will give me complex numbers that have unit magnitude, that is the numbers that lie on this unit circle, and this normalized frequency will correspond to this angle. So for example, if I want to find what is the frequency characteristic for omega equal to pi over 2, I need to take a look at the transfer function at this point of the complex plane. If I want to find what is the frequency characteristic for omega equal to pi over 4, I need to take a look at the transfer function at this point of the complex plane. And if I want to get the frequency characteristic for all normalized frequencies omega, I need to trace the values of the transfer function above this unit circle. And here you have it indicated. This is the unit circle, and these are the values of the magnitude of the transfer function above the unit circle. In this view, I have removed the plot of the transfer function magnitude outside the unit circle so you can see it better. This is the unit circle, and this is the amplitude frequency characteristic. As I told you during the Laplace transform lecture, in practice we do not really plot these 3D plots, but we work with this sketch in the z-plane. And here I can see it too. I can start at this point where the normalized frequency is 0. Then, as the normalized frequency increases, I go up the valley, up the valley, up the hill, and here I arrive to the highest point of the hill. Then I go down the hill, all the way back to the 0. And when I trace the magnitude of the transfer function above this circle, I get this approximate sketch of the amplitude frequency characteristic. And here I have indicated the correspondence of the individual points. So from this approximate sketch, you can see that this is an amplitude frequency characteristic of a high-pass filter. So the system from this example, this system is a high-pass filter with this amplitude frequency characteristic. So this is how you approximately sketch the amplitude frequency characteristic of a discrete system using the positions of zeros and poles in the z-plane. It is similar to what we did with the Laplace transform, but now instead of the imaginary axis, you need to trace the unit circle, and your normalized frequency is given by this angle. On this slide, I will show you that approximate sketching is not just to avoid plotting the actual frequency characteristic in MATLAB, but it is useful, for example, in filter design. Let's say I want to design a filter with this kind of amplitude frequency characteristic. This is a band stop which passes everything except the frequency band around the frequency omega naught. Now this sketch is just an idea of a filter and I want to design it. To design this filter, I can first think how I can arrange zeros and poles to create this shape of the frequency characteristic. Obviously, I need to create these dips on the frequency characteristic, and those are going to be created by zeros. So if I have these dips at frequency omega naught and symmetrically at 2 pi minus omega naught, in the z-plane I need to place zeros at these two positions that lay on the unit circle, and this angle is omega naught and symmetrically 2 pi minus omega naught. But if I had only zeros, the frequency characteristic would be pulled down at these frequencies, but there would be nothing to pull it up like this. To pull the amplitude frequency characteristic up, I need to add some poles. And I need to add them so that they will quickly pull the amplitude frequency characteristic up when I move away from omega naught or from 2 pi minus omega naught, but then they will not pull the amplitude frequency characteristic any further, and I get this nice flat part of the amplitude frequency characteristic. To achieve this, this is where I need to put my poles. Follow this. When I'm very close to this zero will dominate and it will pull my transfer function magnitude down to 0 and create this dip on the frequency characteristic. But when I leave this 0 and move to other frequencies, the effect of this 0 will be compensated by the effect of this pole. One will pull the transfer function magnitude down, the other will pull the transfer function magnitude up. And when I'm further away from them, their effects sort of cancel each other out, so I will get this nice flat part of the amplitude frequency characteristic. Here you have it a little bit more mathematically. The transfer function with these zeros and poles will look like this. This 0 will be here, this pole will be here, this 0 will be here, and this pole will be here. Now let's concentrate on this pair of this pole and this 0. If I have a point in the z-plane which is far away from this pair of a pole and a 0, this difference and this difference will be approximately equal. This difference and this difference will be approximately equal. Consequently, the ratio of these two differences will be approximately 1. And this ratio is this ratio in my transfer function. A similar thing goes for this pair of this pole and this 0. If I'm far away from them, this ratio is going to be approximately equal to 1. So when I put the poles close to the zeros like this, when I'm close to one of these zeros, I will get these dips, but when I'm far away from them, my frequency characteristic is going to be close to 1, and that is how I will get this flat part of my frequency characteristic. Now the poles and the zeros can be expressed like this. This 0 has the magnitude 1 and phase omega naught. Thus, I can write it like this. This pole has the same phase, but its magnitude is a bit smaller. I can write it like this, where I denote its magnitude with this r, which is less than 1. This 0 and this pole can be expressed similarly, but the phase will be 2 pi minus omega naught, or we can use just minus omega naught, which is the same phase. So I can write a transfer function like this. These are my zeros, and these are my poles. When I expand these brackets, I get this, where I can combine these exponentials, and I get this. And remember, when I have a difference equation like this, the transfer function is going to look like this. So when I compare this transfer function and this transfer function, I can directly read the coefficients of my filter. These would be the coefficients of my filter. And you can take these coefficients, put them into MATLAB, and then use the function filter that will implement a filter with this kind of frequency characteristic. In fact, when you plot the frequency characteristic in MATLAB exactly, you will get this. You can see that it nicely corresponds to what I wanted. And if I wanted these notches to be more narrow, I would need to move these poles closer to these zeros. And if I wanted these notches to be wider, I would need to move these poles in the opposite direction. By the way, if you were wondering what the shape of the transfer function looks like in 3D, this is what it looks like. Here are your zeros, and here are your poles. And the red line corresponds to the amplitude frequency characteristic. So this is how you can use the connection between the zeros and poles and the amplitude frequency characteristic to design digital filters. Last, a note on the analytical computation of the frequency characteristic. Remember that for an FIR filter, we could compute its frequency characteristic by taking its impulse response, which were just the coefficients of the filter, and by computing the Fourier transform of this impulse response. This gave us the frequency characteristic. With the IIR filter, it was not so simple. Sure, the frequency characteristic is still the Fourier transform of the impulse response, but for an IIR filter, the impulse response is no longer equal to the filter coefficients. In fact, the impulse response is infinite, so for example in MATLAB, this could be computed only approximately for some finite part of the infinite impulse response. Now with the Z-transform, I can actually show you how you can write an analytical expression for the frequency characteristic of this filter. We know that the transfer function of this system is this, and we know that when I substitute e to the j omega for z, we will turn this transfer function into the frequency characteristic. So when you know the coefficients of your filter, this is how you can compute its frequency characteristic analytically, at least for the second order system. If your system has order m, its frequency characteristic will look like this, which can be written like this. Now, if you examine these two sums, you should be able to identify that these are merely discrete time Fourier transform of the b and a coefficients of the system. So the frequency characteristic of your system can be written as the discrete time Fourier transform of the b coefficients divided by the discrete time Fourier transform of the a coefficients of your system. And by the way, this is being computed when you use the function freeqz in MATLAB.